Okay, so hi everyone, Senan this side, and in this video we are going to solve this Dijkstra's algorithm. The pronunciation might not be correct or will not be correct, but anyways, you are given a weighted, undirected and connected graph of V vertices and an adjacency list ADJ, where ADJ of I is a list of lists containing two integers where the first integer of each list j denotes there is an edge between I and j, and second integer corresponds to the weight of the edge. Basically, you are, rather than having a pair of integers, you're just having a vector for the edge I and for edge between I and j, and the weight corresponding to this. You're given the source vertex and you need to find shortest distance of all the vertices from the source vertex. You have to return a list of integer denoting shortest distance between each node and the source vertex S. The graph doesn't contain any negative cycle because Dijkstra doesn't work in the presence of negative edge weights. So given this, the edge weight is 9, so the source is if 0, so that the distance from 0 is 0 and the distance from 0 to 1 is 9. Basically that is the output that you have to return. So this is a pretty classic algorithm. You can use a queue or a basically priority queue, which is used in this case, and the time complexity is of big O of E plus log B. That is the yep, this also works. So anyways, let's see how do we actually do this. First of all, we declare a priority queue and it would be storing a pair of integers, right? So what this priority queue is having is basically the distance and the node itself. So initially what I did was to first have the node and then the distance, but for that I would have to write a comparator on my own, which I did not want to do. So doing this, we can just use this greater to create a min heap, this priority queue. And what I do is I declare a distance array and mark all the elements as int max. So basically this is helpful for us to to keep track of the visitedness of a particular node. Now what I do is I mark distance as 0, and while the priority queue is not empty, I take out the top element, I remove the top element, and I find the distance of the node from the source node till now. And what I do is I take out the node that we are talking about. Now for all the neighbors of this node, I calculate the neighbor and the edge weight of this directed edge to this node, from this node to this LM. So what I do is I get the neighbor in name and the edge weight as way. And if I say if distance of name, that means distance of this neighbor is greater than the distance till now, like from the source node, this distance plus the edge weight, then I update this because I found a shorter path. And when I update this, then I have to check for the remaining nodes as well, basically the neighbor nodes as well, because since I found a shorter node, the neighbors of this node could lead to a shorter path using the path that I am currently. So I just push that into the priority queue and do this till this while loop or the priority queue ends. And in the end, I just return the distance array. So the logic is basically this: whatever starting node you have, whatever the closest node to that is, would have the shortest distance in any case, because we are using a priority queue, and at the top of this priority queue I would have an element that would have the shortest edge possible. So if I go through the shortest edge, I would definitely find a path which is shorter. So that is the video all about. This was a classic algorithm, so I don't think that it requires much explanation. The only thing is why it does not contain, why negative weights are not allowed, because you could go back and forth between two nodes and still get a shorter distance because it is not bounded below. The only way we are able to do this, because in this Dijkstra, is we know that the distance is bounded below by 0, and that is the only thing we are concerned about. If the distance is negative for any cycle or an edge, we could go into an infinite loop and we would never come out of this while loop, because we would always find a distance such that this quantity gets lesser than this. So that is why we don't use negative edge weights. And yep, that is the whole video. Thanks for watching, and I'll see you in the next video.